Electron shell or electron cloud, it describes the orbital. This term orbital isn't like an orbit. An orbit describes a well-defined shape. An orbital is more of a probability of locating an electron. If this were planet Earth and we got a guy standing on top of planet Earth and another guy dug a hole and he's inside the hole, and this is the center of the Earth and you got a guy in the center, planet Earth continues to rotate in this direction. The guy at the top of the hole can look at the guy at the bottom of the hole, and as the Earth is rotating, they're at the same position. Although standing further away from the center of the Earth, the guy at the top of the hole moves at a faster velocity. He's moving faster than this guy towards the center. Electrons that happen to be further from the nucleus will have more energy. Niels Bohr is a scientist, a Danish scientist, who helps us understand the structure of elements by using hydrogen, which is quite convenient because it only has one electron about in the orbital. And he notes that if you were to change the electron from the ground state to an excited state, if you were to change the radius of the electron cloud, that is being closer to the nucleus and further away, it will have a different amount of energy. Being further away, it would move faster, having more energy. It's important to consider quantum theory when trying to describe the structure of atoms. As Niels Bohr was explaining, from the ground state, low energy, to an excited state, he noticed that there was an amount of energy given off. Quantum theory describes quantities of measurements, usually in chemistry, describing the structure of the atoms. We're talking about an amount of energy. For example, light travels in waves and photons. Photons are little packets of energy. If this happened to be spinning in a nice, perfect circular motion, this electron about the nucleus, if I were to keep doing this with my pen and draw it out, it would give us a shape like this. It will give us a wave pattern. Anything that repeats or oscillates, you can graph it out with a wave. Studying wave patterns really helps us understand why we use this structure for atoms. If we were to plot our wave on a linear point Cartesian graph, it would look something like this. Some descriptions of the wave. When looking at the wave, you have from this location to this location, this is your amplitude. And then from the top of one wave to the top of the next wave, this is your wavelength. Wavelength is represented by the Greek letter lambda. This is a lambda. And a lambda is your wavelength. Frequency. Frequency describes how many wavelengths will pass a point at any given second. Frequency equals 1 over the period. And the period is the time. Time is in seconds. Frequency times the wavelength will give us the speed or the velocity of the wavelength. In this case, I'm using the letter C for our velocity of our wavelength. Why is this review in physics so important to the atomic structure and chemistry? Well, we are looking at the movement of electrons. And the reason why I say shell and not a ring is because these little electrons move so incredibly fast. It's quite difficult to really imagine what the shape is. No one's really seen an atom. This letter C describes the velocity of electromagnetic radiation. Electrons are associated with this electromagnetic radiation. C is also the speed of light. Speed of light, which is a constant value of about 3 times 10 to the 8 meters per second. When considering electromagnetic radiation, these are waves that propagate in nature. And the higher the frequency, the more energy that it will have. So starting at this end of our electromagnetic scale, we have gamma rays. Then we have X-rays. Then we have our visible light spectrum, which has all the colors of the rainbow. Then infrared, microwaves, and then radio. When considering the scale of electromagnetic radiation, your frequency increases in this direction while the wavelength increases in this direction. The shorter the wavelength, the more energy. The higher the frequency, the more energy. Something can have the same frequency but different amplitudes. We will perceive this as more or less intense. Let's consider 2 different waves with the same frequency. This is electromagnetic radiation that happens to be at a frequency that emits the color red. Red is somewhere around here on the visible light spectrum as opposed to blue light or ultraviolet light, which has a higher frequency. But considering the color red, at the same frequency but a lower amplitude, it will be the color red, but less intense. The dashed line represents the same frequency, but a lower amplitude. At a higher amplitude, the red will be more intense, like a cherry red or a fire truck red, and a lower amplitude will be a dark red, burgundy red. Considering the light spectrum and electromagnetic radiation becomes really important in laboratory techniques in chemistry, spectroscopy. When you have a list of different elements and you need to identify the unknown species, every different element or compound will emit a different frequency. And they use spectroscopy to help identify these unknown compounds.